In Chapter 11, we'll be looking at free radicals. When we see a fire, the combustion process is actually a chain reaction, which means that it's self-perpetuating, and this is a process that occurs via free radical intermediates. A free radical forms when bonds are broken homolytically. This means that electrons go equally to both of the atoms. Instead of two electron pairs traveling together onto one atom, we have one electron going to each of the X and Y. Previously, when we've drawn mechanism arrows, we show an arrow with two heads. This shows the electron movement of two electrons. When we do the single arrow like that, this one is the fish hook, or a single fish hook. This is the movement of one electron. So a radical is an atom with an unpaired electron. In this case, one of the electrons from the bond goes onto the X, one electron goes onto the Y, so we have an X radical plus a Y radical, and that is a homolytic cleavage because each of those atoms got one electron. Radical stability increases in the same way that carbocations are stable. Methyl is the least stable. And as we add more R groups onto that radical, it becomes more stable. The tertiary radical is the most stable one before we include things that have resonance stabilization. So the benzylic is the most stable here. So least stable, most stable. And it works in the same way, and we can draw resonance structures, we can better stabilize the single electron. Free radicals don't have a formal charge, but they're unstable because of an incomplete octet. With the primary, secondary, tertiary, we can have inductive forces from the external carbons that donate into that stability, and with the allylic and the benzylic, you can draw resonance in order to do that. If you look at this first one, the allylic position, this one radical electron can come into this bond. This extra pi bond here, one of the electrons can donate into here, and the other electron from here will go on to that carbon. So this is the new bond, and our radical is now on that carbon. So that is resonance stabilized. With the benzylic, we can do the same thing. If I follow the arrows, this stays the same, and that becomes a radical there. And we can keep pushing the arrows around the ring, so these electrons can come in to form a bond here. One of these splits and goes onto that carbon, and the other one goes onto this carbon. So there's a new bond that formed here, and that radical is now on this carbon. And again, you can keep going around the ring. So if we try to draw a resonance structure for this one electron goes here, one of these can go here, and the other one goes onto that. The new bond is formed here from the unpaired electron, and the other one forms here. And we can put one electron here, one there, that one there. So there's a new bond that formed from these two electrons, and that single electron from this pi bond is now on this carbon here. So this would be a more stable radical than the one here, because it's on a tertiary allylic position. If we're looking to identify the weakest carbon-hydrogen bond in this structure here, we want to consider all possible radicals that can form. When a compound is reacted so that it can form a radical, The electrons can be taken from any of the carbons and hydrogens. So the one that you can form initially is a primary one, off the first one here. This would be a primary radical. So one dot here on the one carbon. This is a tertiary radical. This would be another primary radical. And there's no radical that forms this one because there's no CH bond. So we can only form radicals where there is a CH bond. This is a radical that's next to a double bond. This is an allylic radical. This one is on the double bond. This is vinylic. And this is another vinylic one. The most stable radical has the weakest bond. So our most stable one is going to be the allylic one. The most stable radical has the weakest bond. So the allylic has the most stable radical, that will be the weakest bond. You remember when we had formed carbocations, we could rearrange here to form a more stable. Radicals do not rearrange. So there's different types of cleavage that can occur once radicals are formed. First you get homolytic cleavage, where we have a compound that is reacted with heat or light. One electron goes here, one goes here. And we form a radical on each of those. We can also get addition to a pi bond. So we have an alkene, and there's that X radical. One electron comes here, one goes here, this one comes here. So a new bond was formed there. That radical is on the end there. We can have hydrogen abstraction, which is not the same as a proton transfer. One radical comes here. One of these radicals comes from the HR bond, and that goes there. So we form a new bond with H and X, and then the R gets the radical. So that is a hydrogen abstraction. We can have a halogen abstraction. One electron. New bond between R and X, and then we get an X radical. We can eliminate, so the radical from an alpha carbon is pushed toward the beta carbon to eliminate a group. So we have leaving group, one electron comes from here, one electron goes from the X carbon, it goes there. So we now have this X radical and a double bond formed there. And we can couple two things together, which is the reverse of homolytic cleavage. So we have two radicals, can get together and form a new bond. When we're moving electrons around, it can be categorized as an initiation step in the beginning, a termination step where it ends, or propagation, which is the continuing of the electron movement. So initiation is when radicals are created. And that will get the reaction going. If we can't form a radical, then we can't do the reaction. And termination is when the radical is destroyed. And propagation is when the reaction keeps going. Homolytic cleavage falls into the initiation category, addition to a pi bond. We then have hydrogen abstraction, which is still under propagation. We also get halogen abstraction. Elimination still falls under the propagation category. And then termination is coupling. There's a forward and reverse for each of them, so all of these reactions are reversible. The reverse of homolytic cleavage is coupling. So in cleavage, it's broken apart, and coupling, they're put back together. Hydrogen abstraction occurs, and the hydrogen abstraction going backward can occur. We can add to a new bond, or we can eliminate to form the double bond again. Methane, which is CH4, can be chlorinated to give us methyl chloride plus HCl. In the initiation steps for that, we do a homolytic cleavage, and form the two radicals. In the propagation step, the chlorine radical can grab a hydrogen from there. This is a H abstraction. There's a radical here from this one electron, and then we formed a new bond to HCl. So this forms a carbon radical. And then we follow the electrons here. It's going to pull a chlorine off and form a new bond there. So new bond, new chlorine radical. This is a halogen abstraction, and we get the product. So this chlorine radical is free to react with another molecule of methane. In the termination step, this is coupling. We get a new bond that forms here. When it couples, it destroys the two chlorine radicals. We can couple the chlorine radical plus the CH. So that destroys the CH3 radical and the Cl radical, and then we can couple the two CH3 radicals. In a chain reaction, the products from one step of the reactants are used for another step in a different mechanism. So in this process of methane plus chlorine radical, we can form methyl chloride or methylene chloride, where another hydrogen can be extracted and swapped with a chlorine. We can get chloroform, which has 3 chlorines, and then carbon tetrachloride, which has 4 chlorines. Another issue with this chlorination, when you have chlorine plus heat, we can get several products. The side products are difficult to prevent, especially when there is an excess of chlorine present. In order to do a radical reaction, we need to have an initiator. An initiator is something that starts the free radical chain reaction going. We've seen light and heat used that has a delta H of 243 kilojoules per mole. That's a fairly high energy reaction to use chlorine. If we use a peroxide, which we've seen in HBr ROOR, that has a little bit lower energy, and if we use something like an acyl peroxide, that has an even lower energy. So any of these radical initiators can be used to start the reaction. We can also use inhibitors in a reaction that will scavenge or look for free radicals, and that will stop the chain reaction. So oxygen molecules can exist in the form of a diradical, which can react with other radicals. Hydroquinone is a compound that is a scavenger. It will undergo hydrogen abstraction. We get the O radical, which is resonance stabilized. Plus an RH. That radical can react with an R radical. You can get a diradical plus RH, which is in resonance with benzoquinone. If we look at halogen thermodynamics, we have CH3 with a halogen. That forms CH3 halogen plus HX. If we do this reaction with methane and fluorine, or with light, we get CH3F plus HF. Fluorination is very exothermic and is impractical. Iodination is non-spontaneous, and this is not product favor. So if you look at the energy here, it is plus 55 kilojoules per mole. So neither of these are very good reactions to do. Fluorination is not very easy to control, and iodine is just unfavorable. If we're going to use a substrate that's more complex than ethane, we can get a lot of monohalogenation products possible. We already saw that a little bit with the chlorine products. If we're looking at propane, we have these 2 hydrogen atoms that can get picked up, or these 6 hydrogen atoms here. So for chlorine reacting with that, you can get this product, or this one here. This is about 60% yield. This one is 40% yield. For the chlorination product, the actual product that is favored is chloropropane, because that is a more stable radical than the primary one here, which you can see in this graph here. The secondary has less energy to overcome and gives a more stable radical. The primary is higher energy and a higher energy product as well. If we do this reaction with bromine, this occurs in 97% yield for the secondary and 3% yield for the primary. So it's much more stable, and there's a lot more selectivity if we use bromine. If we add a carbon now, we can get this product, or this one. This is about 65%. This is 35%. This is 100% yield. This is 0. So bromination at the tertiary position happens 1,600 times more often than the primary. Formation of the radical is similar to the alkane itself before it was formed into a radical, and the products are slightly lower in energy. But when we go through the formation of the bromine radical, the transition state is a lot more sensitive to the nature of the substrate during bromination. So with the diagram for chlorination, there's only a small difference in energy between the transition state that leads to the primary, second, and tertiary radicals. And in contrast, the energy diagram for the bromination shows a large difference in energy between the transition states, which leads to the secondary, primary, and tertiary radicals. And so bromination shows greater selectivity than chlorination. We're going to try to predict the product of this reaction with 2,2,4-trimethylpentane. We start with drawing pentane, 2,2,4. We're going to react it with Br2 and light. If we draw all the possible radicals that can form, and this primary, these are all equivalent, so we can also get one here. Bromination at the tertiary. This is primary, primary, secondary, tertiary. This will be the most stable one, because that forms the most stable radical. We will not form a radical here because there is no hydrogen to abstract there.